So I want to welcome you to another Earth2Class. I think we're up to 209 now. I want to welcome back Remi from the RRI. I don't know how many of you were here for Remi's talk last year, but we've made some changes. So I want to share my introduction with you. As you can see from the title, it's a brief history of cartography and an introduction to the RRI map and climate data library. We think the very first maps were probably stick-drawn images in mud to show fellow hunters and gatherers where kill sites of berries were located. This eventually led to the development of the compass points. I discovered this week that east comes from the ancient word that means dawn. North comes from an ancient word that means left, since north is to the left of where the sun rises. West comes from an ancient word that means night, where the sun sets, and south derives from where the sun is during the daytime. How many of you knew that? Okay, so I've done my part and taught you something today. As societies develop, people develop maps to orient themselves with respect to other places. This is one of the very earliest maps from the 6th century BCE, which includes Babylon and Susa. And this is an ancient Greek map from Anaximander. It shows lands around the Mediterranean. From an early age, we learn to identify shapes and positions. Do you see there's one state that's marked with an XY? Anybody know what that is?
South Dakota.
How do you know that?
I know my states.
Okay, so who's ever been to South Dakota?
Why would you want to?
Oh, this.
For most of us, we've never been to South Dakota. We've flown over it. So the idea that that is South Dakota is taken on faith. That's what we often do with maps. We take things on faith based on their shape and location compared to other places, and then assume they're real. I had lunch on Saturday with my best friend who I've known for 61 years now. And we were looking at a map in the deli, which showed apparently the best kosher delis in every state. There is none in South Dakota, so South Dakota does not really exist. Okay, getting back to some more serious stuff. In cartography, we use map projections, which is a way to flatten the globe's surface into a plane. This involves systematic transformation of latitudes and longitudes from the surface of the globe onto a flat plane. As all of us who have taught know, projections of a sphere onto a plane distort the surface in some way. Depending on the purpose of the map, some distortions are acceptable, others are not. So this is a map from Eratosthenes. We drew an improved world map over Anaximander and incorporated information from the conquests of Alexander the Great and his successors. Asia became much wider. Eratosthenes was the first cartographer to include parallels and meridians. Here's another map. This has Africa down here in the bottom, Asia to the right, Europe to the north. And this is from about a year ago, but one of the other things about many maps is that we use color coding to represent differences. So this was a very early COVID map. This is a Ptolemy map from about 150. And as we know, Ptolemy's influence lasted for centuries. This was a map from a classical work on geography and may have been based in part on the journey of an Archbishop of Canterbury to Rome. This map, although I can't really see it, is allegedly the work of a very early Spanish cartographer. One of the first maps that shows the Americas. And exploring the Americas was the purpose of things like Henry Hudson's voyage to the New York area, which laid claim to New Netherlands. This is a very early map which has the Americas on it. You'll see parts of Brazil over here, Caribbean, and a little part of Florida. This is one of the early Mercator maps. And as this says, Samuel Dunn was a British mathematician and astronomer who made maps in 2 hemispheres. But you'll notice there's no Antarctica, which as far as the Europeans was concerned, was not discovered until the 1700s. Although other parts of the world had an inkling that Antarctica was there earlier. From the 16th to the 19th century, there were many voyages of discovery, including James Cook, before he got involved with McDonald's. His ship was the HMS Endeavour, and then later the HMS Resolution. Resolution is the namesake of the Geordes Resolution drilling vessel. Another important voyage of discovery was the Beagle under Captain Fitzroy, who had Charles Darwin on as naturalist and Conrad Martins on as the artist. Last month, I mentioned this map, which was Franklin's Gulf Stream map. Eventually, people realized that they could show the world more accurately with globes, which are 3-dimensional. Problem with globes is that the scale has to be very, very small. Globe can't be too large. And Lamont's contribution to cartography is basically related to Marie Tharp. Marie Tharp was able to use echo soundings from various ships that had gone across the oceans and developed a technique to take the echo soundings, turn them into what looks like a 3-dimensional map. So we now have these, what are called Heezen-Tharp maps, because Bruce Heezen was the principal investigator for the grants that supported this. Although Marie did all of the brain work and work. I got word this week that a friend of mine is starting to write a play about Marie Tharp. Renee, it's Flipper. So we'll see whether that becomes a Broadway hit in a few years. We can even map places we have rarely been to, like the moon and Mars. And one of the other ways in which we can use maps nowadays is through digitalization. We can layer maps so that we have some information in one map and another information in another, and we can put them all together. And then we have special purpose maps. This has information about COVID cases, again from about a year ago. And finally, we can map things that don't really exist. Although the title says sea surface temperatures, if you look below it, it says departure from average. So the different colors represent anomalies or differences from the expected value. With the final points, I want to introduce the IRI, Lamont Climate Data Library. IRI is an institute within the campus of Lamont. The original PI was Martin Blumenthal. This is Martin. This is some of his early stuff. Unfortunately, Martin Urbano passed away at the age of 59 in 2018. Anybody who wants to go on later and read more about him, I have the memorial information here. But Martin gave the September 2000 Earth2Class. This is an example of a page on there, and with that, I finish up and I turn it over to Remi, and welcome Remi back to Earth2Class. Okay, Remi.
Thank you, Michael. Hi, everybody. So my name is Remi Cousin. I've been working at the II for over 13 years, and all my career, which is a bit over 15 years in climate sciences. Even though I'm not a climate scientist myself, I'm a data guy. And to complement a little bit on what Michael said about the II, so this institute is called the International Research Institute for Climate and Society. And it was founded in the 90s when climate scientists realized that when El Nino or La Nina developed in the Pacific Ocean, as you've seen in one of the latest maps that Michael showed, they were able at a low cost in terms of computing to make very skillful so-called climate seasonal forecast. That is to say, they were able to predict a few months ahead if rainfall seasons, especially in the tropics, were going to be wetter or drier. And out of this, they created the institute that was originally called for climate prediction and is now called for climate and society. The goal of the institute is to deliver this information about seasonal climate forecasts to people who can make use of it. So if you can predict that the rainfall in the Sahel in Africa is going to be wetter during the growing season, then small farmers who rely exclusively on rainfall to grow crops, then they can take advantage of that by, for instance, buying fertilizers. Or if you can predict that there is more likelihood that they're going to have a dry one, then they can possibly change their livelihoods for this season, or governments can take action to protect them. So that's the whole idea of the II. It's funded mostly in part through traditional federal agencies, science agencies of the US, like NOAA, NASA, NSF, and but also by because of its mission by, let's say, development agencies, so USAID, UN organizations like the World Food Program, and so on. And so, for historical reasons, the II has also been the host of the data library, which was started by Beno, who was my boss and my mentor until he passed away. Which is a tremendous collection of hundreds of climate and climate-related datasets that are available online, mostly initially for scientists, but it's publicly available. So with a bit of knowledge, one can extract and use those data as they wish. Now, this requires some knowledge, either in computer to download data, in programming if you want to make analysis, in statistics if you want to know which analysis to make, and so on and so forth. So we have also another thing that we call map rooms, which is what we're going to look at today, which is a website where we've pre-analyzed, pre-selected data sets to make maps, graphics that are available by just a few clicks to any kind of users. So my belief is that this resource could be useful in the classroom for your pupils and students to be pointed to seek information on this or that topic. So even though I do have a good deal of teaching in the sense that we are transferring on our tools, science and technology to our partners around the world. So I'm teaching them how to use them. But it's a different story than a classroom. So I mean, with in the educational program with students and pupils. So hopefully what I'm going to show you is going to inspire you in using those tools, maybe for your classroom. I'm going to do a live demo. We're going to visit a few of those map room pages. I'm going to try to go through a bit of a storytelling so that it's appealing. So we're going to look first at a few maps that give us a sense of what we call the mean or normal climate. Then we're going to look at other map rooms that show us how the climate varies historically from its mean or normal condition, which is what climate scientists care about. They want to understand how climate varies year after year from time to time, and hopefully predict it so people can be prepared to a change for a given season. We're going to look at some monitoring tools that allows us to see the state of the climate now, how it's different from the normal. And then we're going to look at forecasts, again, seasonal forecasts. So I'm going to share my screen now. You are very welcome to interrupt me at any time to ask a question, or if you prefer to raise the hand through the Zoom tool, I think I should be able to sit and give you the opportunity to speak. I probably won't look at the chat because I don't know very well how to speak and read at the same time, but I can speak and be interrupted at the same time. That I can do.
I'll try to monitor the chat for you.
Okay, okay. So let me share my screen. Okay, we'll get rid of this. We're trying to move that. So that's me here. And now we're going to, so you see this is the homepage of the data library. Is that what you're seeing? Yes. Can someone confirm that you are seeing?
We are seeing it.
Okay. All right. So as I mentioned, we're going to go through the so-called map rooms. There are other things on this homepage that you can see. This is where you actually found the data directly that the map rooms query. And then you have a bunch of helping tools to understand how to use the website. So there is a bunch of things in there. We are obviously not going to go through all of them. I'll just move on and then when time is up, we'll stop. And you can see that they are organized by sections which are either thematic or sometimes related to a partner, like the Red Cross here. I'm going to go into the one that talks about the climate in general, the first one here. And we're going to look at what we call the normal climate or climatology. So here I'm still navigating the website, and I'm going to go into the selected point climatology, which is going to show me so a word on the content briefly. So we have here a map that is a climate classification. It's not very important. It's static in time. And here we have average over the whole globe. We have what we call the climatology. So climatology is for every month. For instance, here July, the average value of precipitation over 30 years. So currently, we do the average over 99 2020. That's World Meteorological Organization standard to use the past complete 30 years to define a normal climate. And here we have a few variables. We have precipitation, temperature, wet day frequency, and ground frost frequency. Because this by default shows an average over the world, we have very little variability across the year in precipitation. And we have some in temperature, which is mostly due to the fact that we have a lot more land mass in the northern hemisphere than the southern hemisphere. So the global average of temperature makes it our summer hotter than the winter. Okay. Before I talk more about the content, let's talk about a little bit of the interface. So all the map rooms will look the same. You would typically have a top bar that allows you, I never know what to do with this, a top bar that allows you to make changes to the map room content. Then you have the main part, which are typically a map and one or more local graphics. And then you have text, because as much as you need a legend to explain what a map shows, we need text to describe what map room shows. So you would typically have more or less elaborate text that describe what is being seen. Then you typically have another set of text for dataset documentation. So this explains what data have been used to make the map and graphics. And I won't click this because it will take me elsewhere. It's going to take you to the programs that make those analyses. So if you're a programmer, you can look into that. And then you have a contact us. You can feel free to write to this email to have any questions about the library and map rooms, or to write myself if you have any. So you will find those things typically in all map rooms. Then when you mouse over the map, you see that controls are showing up. So one control is a so-called layers control, where you can choose to uncheck or check different layers. So for instance, here we have the countries. I could decide to remove it. Okay. You have a share button that will take the map to different tools. So I'm not going to explain each of them, but Evernote is a note-taking online application. Tumblr is for blogging. Pinterest is another kind of blogging focusing on images. Because this is a map, we can also send this to Google Earth or to an ArcGIS software. You have a download button that allows you to download the image in various formats that you may or may not be familiar with. And you have the I button that takes you to the code again that makes this map. So I'm not going to click it because I want to remain here. Okay. Typically, you have the capacity to zoom over a map, either by predefined zooms. So here I'm going to pick, for instance, North America. You will see that so the queries are done live. So there are servers at IRI in Monel on Lamont campus that are being queried as I make requests. Or you can drag a box to make a tailored zoom. So here, right, and that's more or less it about functionality. We will find all those functionalities in all the maps, more or less, in the map rooms. The specific map room is showing local graphics for an average over the map. So now we have like a wide Northeast North America. But typically, you can also click on a point to get that very point information. So here I clicked somewhere, near the Hudson Valley. I have a little pin here that helps me locate where I clicked, and I have the coordinates of the grid box that I clicked. Okay, so it's a half a degree resolution, which is why I see 74 west, 73.5 west, 40.75 north, 41.25 north. Now I have the information for this very location. So we can see that in the Hudson Valley, there is very little variability over time, over the months of the year in precipitation. And we do have, as we know, very big variability in temperature. Okay, with very warmer summer months and cooler winter months. Okay, so this is what we call the normal climate. So every time you hear about, it's also true in weather science, whether they talk about projections or forecasts of any kind, and they talk about anomalies, or they talk about going away from the normal. This is what people here mean when they talk about the normal. It's the average condition in a given month over 30 years. Now, let's check another part of the world. You can cancel a zoom by clicking the very first control that says zoom out, so that I can see the map of the world again. And now I'm going to go to the side I was talking about. I'm going to put back countries to help me localize things. And I'm going to click in the Sahelian bar here, I mean the zone. And so here you can see that they have a very different normal climate. So they have rainfall only during the June to October season, basically. And so it's easy to understand that if you're a small farmer in this part of the world, you rely on this to feed your crop, basically. And so if this thing changes, you may be, your livelihood may be at risk. There's another kind of variability for temperature. And yeah, so if we look further south into West Africa, so here I'm going to click into, I think that's Ivory Coast here. You can see that they have a very different, especially in precipitation pattern. They have two seasons. They have two peaks in May, June, and then another one centered in October, typically. Why is that? Is because it's, you know, the Sahel region is a monsoon kind of system where you have clouds that form in the tropics near the equator in the south, and they go up north, and eventually they go back down south in the ocean. And so that's why you have two peaks in the south on the coast, because you have the first peak when the mass of clouds go north first, and then they go back south and they have the second peak. And that's why you have only one peak in the northern part, because they only get the clouds go north and then eventually they go south. That's the peak they have here. All right, so these are a few examples of understanding normal climate conditions around the world, that you can click any point or zoom over any area to get an average over this area. Now, let me check what I want to see next. All right. Now, the whole thing is that these values, they are just the normal ones. Every year, every month of July, it's not exactly that falls, that happens. So the goal of the climate scientist is to understand this variability. And the first thing to do to understand something is to try to observe it. So I'm going to show you another map room called the timescales map room that is a bit more statistical in its language, but hopefully that won't be an issue. And what this does is that it decomposes the 20th century climate into three components. One that we call trend or climate change, associated with the climate change. One that we call decadal, which is 10 years period variability. And one that we call interannual, year-to-year variability. So here we have, again, it's showing the average for the whole globe by default. And you can see here I have a few new controls. So each map room, we have different controls depending on what the purpose of the map room is. And you can see that we have, by default here, we are looking at June, July, August season, okay? So we are looking at how the rainfall, sorry, I clicked temperature. We're looking at how the temperature varies year after year for the June, July, August season. So each point you see here in the black curve is what we have observed averaged over the world. So you can see that there is interannual variability. You can see there is a trend. And maybe you can see that there is longer, slower frequency variability. So this first point here is 1900. You can see the mark here for 1920, 1940, and so on up to 2020, more or less. Okay. So the black curve is the variability from the normal we've just looked at before. Okay. So you can see that it can vary from that normal. It can go away up to 0.5 degree, and here up to 1 degree or so in the maximum. And so here what this map room tries to explain, it's the different components of this variability over a century of observed data. You can see the first component is this red curve, which is associated with global warming. And so it's not a surprise that it's a big part of the variability over the world as we observe it. Then some fancy statistics identify the so-called decadal variability. So you can see it's smoother, slower variability. And then we have the year-to-year variability independent of this green and red curve. Okay. And here you have the percentage of the contribution of each to how things vary. So when you look at climate, temperature, obviously the main driver of variability is this big trend due to the global warming. But you can see that year after year, you may have very cool year or very hot year on the annual basis. So these are the things that climate scientists in particular at II are trying to understand and potentially predict. So here again, you can click a point or zoom to see local behavior. It's also going to do an average over the zoom-in view until you click an actual point. So you can see here the resolution is a bit coarser from this dataset source. We have bigger grid boxes. And here I clicked again our area here in New York City, around New York City. And so we can see the global trend of global warming is very important. And we have the interannual and decadal variability. Okay, so this is how the climate varies, at least temperature, over the 20th plus century from its normal condition. Now, let me go back to the globe, and then let's look at precipitation. So I'm going to navigate to the precipitation version of this same analysis. And what's very interesting to look at when you do the same, so maybe I should say a word, you see there's a lot of white. So that's, so the data product used here is using observations, and then it's doing some interpolation technique to grid it so that you can make nice maps. However, we must out areas that don't have enough data to really support the analysis. So that's why you have big blanks. Obviously, you don't have a lot of data, for instance, in areas where there are few people, like the Amazon, or where countries are too poor to really maintain a network of stations, like in some countries here in Africa. Whereas, for instance, Europe and the Northern Americas have plenty of data, something to be aware of. Now, what's interesting when you do this analysis for temperature, for precipitation, sorry, you can see that there is no response globally to the climate global warming. And this kind of makes sense because what's happening with global warming is that we are increasing temperature in the atmosphere through the green gas effect. But there is still the same amount of water on the Earth. So globally, there's no increase in water availability. And rainfall globally doesn't have a trend as temperature has. We're going to see later that, however, locally, you may have a trend due to global warming because the climate is evolving because of this warming. And so patterns of rainfall are shifting around the globe. So even though globally you have the same amount of rainfall that falls, it doesn't necessarily falls in the same places that it used to. Okay, and same thing here. You can see that there is a decent amount of variability that is due to so-called decadal low frequency variability. And you have year-to-year variability. So now we can see that the most important component of the variability for rainfall is the year-to-year variability. So that's why, even though it's important to understand and focus on climate change for certain topics, it's also important to understand that, again, if, for instance, you're a small farmer that relies on rainfall somewhere in the world, it's more likely that your livelihood is going to be at risk, or it's going to be altered by year-to-year variability as opposed to the long-term trend of climate change that impacts them in the next decades. Okay, so let's have a look again at some localities. So I'm going to go back to New York to see what it looks like. Up, clicking this grid box. So you can see that here locally there is a slight trend, even though it's only 2%, so it's kind of flat, positive trend, and some 10-year variability and a lot of year-to-year variability.
Remi,
Yes.
we see that there's a note here, the trend not significant at 5%. Could you explain what that means?
It means that basically, so the trend here, if it was just by chance, if we would just, if this rainfall data was just random data that we pick number randomly, we would not see a trend at all. So this trend that we see here statistically could be just chance. It's in the margin of errors. That's what it means. So basically, we see a little plus. We do see a slope with our eyes, but the slope is kind of random. Okay, now let's go back to the Sahel. Sorry, I'm taking that example because I find it easier to tell a story about it. So I'm going to zoom over Western Africa. So you remember that in that region, they have rainfall only in this season, June, July, August, basically. I'm going to zoom over the boxes here, and we're going to see what it looks like. So here, even though, again, the global average has a flat trend, the New York average has an insignificant positive trend. Here in the Sahel, we do have a global change response in rainfall that is negative, and that is represents basically 10%, 11% of the variability of the whole thing. And what's also very interesting to see in this part of the world is that they have experienced very big 10-year cycle, 30-year cycle variability. And you may or may not have heard, and it actually is true, this extends towards Ethiopia, even though there's not enough data to have Ethiopia there, but you may recall the 80s, where there were lots of things in the news about drought and famine in Western Africa, in Ethiopia, in Chad. And this is because of this big change in rainfall, long 30 years from like the 70s to the 90s, they had below normal precipitation due to this big 30-year cycle. Whereas the 30 years before that, they had actually very nice positive rainfall anomalies, at least driven from those 10-year cycles. So you can imagine if you're again, I'm going to take the same example. You're a small farmer in Niger here or Mali, and you've been used to having this level of rainfall during the season. You have a livelihood, you grow crops that rely on that. And then for the next 30 years, everything goes down to this constant recurring drought. Then you basically, you're screwed and you go into famine and drought. You can see that it's been recovering since the late 90s. All those things are subject of studies, various reasons why this is happening. And they are back to normal, which is still, normal is still much less than what they used to experience in around the 50s and the 60s. Okay. And in spite of, they had to face this big cycle, but they also had the year-to-year variability. So for instance, you can see that here, even though they are into normal condition, the year, I don't know which year that one is, maybe 2002 or 1, was particularly dry. So most likely small farmers were hit during that year. Whereas the year after, they had a rather good year. Okay, so these constant fluctuations year after year obviously affect their livelihoods. And you can argue also that, for instance, the very bad 30-year cycle they also had some good years that possibly compensated the difference brought by the 10-year cycles. So anyway, my point is that those three components, the trend, the 10-year cycles, and the year-to-year variability, they are all worth looking at if you're trying to understand the climate and if you're trying to provide an information that is useful to a specific livelihood. Example given, a rain-fed farmer in the Sahel. And so, right, so I think that's all I wanted to say about this one. So now we understand that you have normal conditions, which we define as the last 30-year average. And we try to understand how the climate varies from those normal conditions. And we do see that whether it's due to large trends from anthropogenic forcing, whether it's due to natural variability in the system at lower frequency or at high frequency year to year, it varies a lot from this average, from these normal conditions. Let's now have a look at some monitoring tools. So I'm going back up in the website and I'm trying to remember where this is. I think it's atmospheric circulation. Nope. See, there's so many things that here I go, precipitation, seasonal, and we're going to look at seasonal anomalies. I'm going to zoom out back to the world. So this is one of the monitoring map rooms. You've seen that there's a bunch of them. And you can see that now it's showing what we call anomalies. So we are looking at departure from this, again, 30-year average in millimeters. Here for the last season available. So we are October 30th. So the last season available is July, September 2021. In a few days, if you go back to this page, you will see the August, September, October season. And so let me just have a bit of water. What do we see here? We see that, for instance, so near New York, we had a slightly wetter summer than usual, even though just south of it, it's drier, so possibly close to normal. We can see that Indonesia, the Philippines, part of the South Philippines, they've experimented wetter summer. Our Sahel region on the coast has had wetter season as well. What is white means zero, so no departure from the average. So everything that is white was normal. I'm just back from France, where I'm from. I'm sure you figured that out. And it was a gorgeous sort of Indian summer there, even though we don't call it that over there. People kept on telling me they had an awful summer, but if you look at data, at least in terms of rainfall, they basically had normal conditions over the July season. So I also had normal conditions, and we can see Venezuela and Colombia had very dry July, August, September season. Okay, so this map updates every month with a new season, and there are many other variables or ways to look at these that are available in those map rooms. I don't think there is a click option on this. No, so here is just a map. There are many ways to look at data. Here we see the departure from this average in millimeters. There's another analysis that people like, which is called SPI, Standardized Precipitation Index. And it looks at the same thing, except it's instead of expressing it in millimeters, it's expressing it in standard deviations from the distribution. So that means is that where you see -3, it means that you got rainfall 3 standard deviations away from the average, which in statistics means very far, very, very far from the average. And so people will translate that in English into extremely dry conditions. So if you remember the previous map, we had patches of green over the coast of West Africa, and it's actually a light green, so they didn't go that far from actual the normal conditions, except from this part in the Niger-Nigeria border, where they did have 2 to 3 standard deviation away from the normal conditions. The very dry in millimeter that we saw in the previous map in Colombia and Venezuela does confirm that it was extreme events, an extreme season in terms of how dry it was. Okay, so same data, different analysis, different story. You may care about the number of millimeters you get or you don't get, but you also may care about how extreme the events were, depending on what question you're trying to answer. Okay, and here, yeah. So that's 2 examples of monitoring. All right, now let's talk about sea surface temperature. Let's see where this is again. Yes. So sea surface temperature. We're going to take the seasonal one as well. And so this is looking at the same thing that Michael showed at the end of his talk, so-called seasonal sea surface temperature anomaly. So again, what you see here is not actual temperature of the ocean surface. It's how much is departing for this normal condition again, so the 30-year average for a given month or a given season. So wherever it's white, it means you're within 0.4 degrees of what the ocean temperature typically is in this season. And then as it gets redder, it means it's hotter, and it gets bluer, it means it gets cooler. Why do we care about this in terms of monitoring? It's because the oceans are, if you wish, they are the radiator of our atmospheric climate. So they provide heat and moisture to the atmosphere. And so a lot of, especially in the tropics, it also spills over to the higher latitude. A lot of the climate variabilities that we've seen in our timescales, map from the year-to-year variability in particular, and the decadal one as well, comes from things that happen in the ocean. And the predictions that are made by the IRI are also a lot driven by the ocean's variability. Where did you see EOS? Ruben.
Yeah, it was in one of the articles before.
Oh, it's the name of the journal. I think it's, maybe Michael can help me with that. It's a AGU paper. It's Earth Observation System or something like that. It's the name of the journal that publishes papers.
Okay, thank you.
Yes, so sea surface temperature, and in particular the one in the tropics, is the one that is driving a lot of the interannual and beyond variability of the climate, because it's shifting where rainfall evaporates, therefore where clouds form, and then those cloud formations trigger circulations over the globe, and then rainfall falls or not here and there. Here, I will not be able to interpret much of what's being shown. We do see a patch of warmer temperatures here in the Pacific. Maybe one thing that is interesting, you may remember that we were seeing wetter than usual rainfall in the coast of Western Africa. It turns out that the sea surface temperature near its coast is warmer. So it's very possible that it's warming of the sea surface temperature here that has caused the region to have a wetter than usual summer, because there has been more evaporation, and so bigger cloud formations, and therefore more rainfall in their local area. Now you may start to understand why, even though when you make a global average, for instance, you see no trend in rainfall, but then when you look at a specific location, then you have specific localized physical physics that are going on, and you have different patterns. Now let's talk about El Nino, La Nina, ENSO. I'm sure you've heard of those terms before. So ENSO means El Nino Southern Oscillation, and it's a big event that happens in the tropical Pacific, where sea surface temperature go back, invade warm sea surface temperature invades the eastern part of the ocean and shifts all those patterns of rainfall in the atmosphere as a consequence. And so it's the main reason why AI was founded, because this big signal is staying for up to a year and a half. So it's shifting conditions for rainfall over a long period of time, and thus you can make nice predictions or skillful predictions. The biggest contemporary El Nino recorded was in 97, 98. And so I'm going to illustrate that. So we've not used this control so far, but you can see that we are showing here July, September 2021. I can go back as far as November 1981. So you can also navigate, even though this is meant to be a monitoring tool, you can also navigate history in most of those map rooms. So I'm going to go back to 96, a little bit before ENSO of 97, 98. And I'm going to make an animation clicking on the arrow here that takes me to the next time step, so that we can see the development of El Nino this year. So in July, September 96, we have a bit of anomalies here and there, but nothing big really, and you will see what I mean by that. So I'm going to click the arrow several times. You can see that now we are in August, October 96. So we're going season through seasons, 1 month at a time. You can see the anomalies are going to develop. Here, you can see now you have warm anomalies that start to develop in the Eastern tropical Pacific Ocean. And you can see that it's going to be bigger and bigger and bigger as I go through the end of 97. And so what happens is that, so here now we have maybe 5 degrees more than normal conditions in the heat in the middle of this of the Eastern Pacific Ocean. And you can see it's a big pattern. It has started already 6 months ago from this map, and it's going to last longer. And this big pattern, as I mentioned, there is documentation in the map rooms about this, shifts all the atmospheric circulation, especially in the tropics. And you may remember that usually when there is, or you may have heard in the news, when there is the El Nino like this developing, you hear about floods in Peru, in Bolivia, whereas you hear about dry conditions and fires in the Philippines or in Australia. I'm going to keep going the time series, and you can see now the system El Nino is weakening. And we're going to have the other part of the oscillation, which is La Nina, which is that those warm waters are now going to go back from east to west, like a boomerang effect or like a seesaw kind of thing. You can see now negative anomalies are forming here on the center and east, while hot anomalies are forming on in the west. And that's going to peak somewhere at the end of 98, beginning of 99, I believe, or maybe 99, 2000, let's see. So typically La Nina is much less stronger in intensity. We don't go as far in negative values as we went for El Nino in positive values. And I think that's basically it. Okay, so it does a cooler than usual Central and Eastern Pacific Ocean and warmer on the west. And so typically when you have La Nina, it's the other way around. Then you're going to have fires in California and you're going to have floods in Australia. So what you've seen here in part explains all the variability we've seen in the interannual graphics we've seen in the previous map groups. Okay. Something I want to show to another way to look at this, which I find interesting, is what we call the thermocline. So I'm going to go now to the ENSO specific section. So the things that I explain a bit very quickly, you can find more about it. You can see in the what is ENSO section how the patterns of rainfall shift based on where the warm pools of water move from east to west in the Pacific Ocean. So you have more explanations of that in that section. I still want to look at data instead, and I'm going to have a look at this thermocline thing. So this is an animation of the past 12 months. What you see here is, here we have depth. Unfortunately, the ticking is missing. And here we have the surface. Here we have the Eastern Pacific, the Americas in the East, and on the West we have Asia. Okay, so it's a section done at the level of the equator in depth of the sea surface temperature. What you see is that it's warm on the West and at the surface and less warm on the East. And obviously, as you go deep, you get cooler because you have less warming from the sun, basically. And you can see that in the past 12 months, it's moving a bit, right? Why is it like this? So this kind of normal-ish conditions, it's because of the rotation of the Earth, the winds at the level of the equator, they go from east to west. So as the sun is warming the surface of the water uniformly, the winds are pushing the warm surface waters from east to west. So that's why you have the warm waters pushed towards the west. I have a big pool of warm water and cooler on the east. Okay, so that's the main reason why it behaves like this. So now we are going to, so this map actually doesn't let you go far back in time. So I'm going to cheat and I'm going to click the I button that takes me to the program that makes this, this animation. You may not see the difference, but we've moved to another part of the data library now. This is a program that makes this animation. And I'm going to alter it because I'm knowledgeable in it so that I get the chance to go further back in time. Here we go. So now it stopped moving. It shows me the first data point, which is January 1980. Okay. And I'm going to do the same thing that I've done before. I'm going to go to July 96. And what we've seen at the surface is the temperature move east and then back west. You're going to see what it does, how it works, what happens, sorry, when you look at this way of looking at data in depth. So in July 96, conditions are normal and the pool of warm waters are here on the west. And then we're going to keep going month after month. All right, March 97. So you can see the extension of the pool of warm water is starting to move east. Now it's at the center in September 97 of the ocean. It's going to reach the east in February 98. You have a bit of variability in there. I'm kind of doing this live, so. And eventually, now we're in 99, so we're going to see the counter effect of La Nina, where the warm waters are going back west. And so that's basically what's happening during El Nino. That's why people call it an oscillation, because if you look at, this is what they call the thermocline, which is the gradient of temperature, which forms here between the warm waters and the deep cold waters. And so this thing is actually, it's always moving like a seesaw balance. And then when there's El Nino, it moves all the way, pushing the warm water east and La Nina back west. Okay. That's what I wanted to show about sea surface temperature and ENSO. We've done ENSO doing that. Okay, so now let's look at forecasts. So all those things can be translated into forecasts. So I'm going to show you the state-of-the-art forecast that IR has been producing for several decades, called seasonal forecast. And I realized a lot on the things you've seen so far. All right, so the latest forecast was made in October 2021. And it's forecasting, sorry, there's pop-up boxes here. It's forecasting the next season, November, January, coming up, okay? And those forecasts are probabilistic. So here, this is about precipitation. And what it's telling you how likely you are going to have a wetter or a drier season than normal. The best way to illustrate this is, let's click an area where it's dry, like Uruguay over here. And this is what is actually forecasted, just those three values. So what is done is that we break the history of rainfall into three equal parts. The third driest year, the third wettest years, and for this season, and in the middle, the normal years. Okay. And we make a forecast, and the forecast is going to tell us the likelihood of falling in one of the three categories. So when the forecast doesn't know anything, it returns white. I'm going to click a white area here in Russia. It says 33% chance to be in either of the three category. Okay, if you divide something in three, if it's random, you have 33% chance to be in either. Here we have, if we go to the Uruguay forecast, oops, I probably clicked the ocean. So I'm going to zoom so I can see something. Here the forecast is telling me I have almost 60% chance to be below normal, we have 60% chance that the coming season is going to be among the 30% driest years on record for this point in Uruguay. While we have 10% chance to be a wetter among the wetter years. Okay, so when you don't know anything, you have 33% chance of having a drier year. So here we're saying, well, you don't have 33% chance, you have almost 60% chance. So that's the whole game of the IRIs. When you're able to say that, what can you say to institutions, individuals, governments, what have you, to take that information in form of risk and translate it into something that they can take action upon. If we look at the global map again, so we can see our friends in Florida may experiment a drier season than usual, as well as in Mexico. And there's not much being said over the Sahel, but that's because there's no rainfall in November, January season that is forecasted. So there's basically nothing to say. The Philippines have a very wet forecast. You can see here the probabilities have shifted well above 60% chance to be in the wetter tercile or wetter years in the Philippines.
Remi, could you talk a little bit about how this information gets to decision makers in various countries?
Yes, so this is publicly available, so obviously folks can just consult it. And then typically, it's difficult to make a decision out of this type of information. So usually when we have projects with partners in countries, first we try to make a forecast that is even more skillful for their area of interest. So here we have a global forecast, so it's trying to be good everywhere. And as a result, it may not be as good as if you were focusing on a region like the Philippines. And then we help them trying to interpret those results. So here in the Philippines, they have a wetter season expected. So maybe they want to be careful about risks of floods. The Ministry of Health might want to consider being prepared for a more active than usual malaria season. Whereas the farmers, as I mentioned earlier, they might want to invest in fertilizers or to boost up their production because there are not going to be any lack of rainfall. It's important to understand also that this is about the total rainfall in the 3-month season. And so it doesn't say anything about when in that season the rainfall is going to fall. For a farmer, it matters. A farmer wants a bit of rainfall every day during its growing season. It doesn't like at all to have everything falling during a couple of weeks and then no rainfall. So we can also tailor forecast to look at other variables than the total rainfall season, such as the number of wet days or identifying what we call dry spells, which can be more relevant to a, for instance, farming decision. And all those tools, we report them to institutions locally, usually the meteorological service locally, so that they can then do the things themselves and produce those maps. Now, probably we're getting to the end of this, so let me just see what else I had in mind. Yeah, I want to show you the same forecast, but this time it's not showing 3 categories, it's showing a full distribution. So for those who like statistics, I'm not sure, I don't know how old your students are, but you can see the forecast. So this one is a bit behind because we had an update recently, so it's going to catch up likely next week. So the last forecast was only made in August. And if we go, if we go back to a wet area, now it's showing me what we call the full distribution of the rainfall. So in black, you have the distribution that is expected for this point that I clicked. So the expected rainfall is basically just under 400 millimeters. And then you have, a bit of chance to be above 1,000 millimeters in this part of the world. And then the green one is the forecast. So the forecast has shifted way back to wetter conditions. Now it says the most likely value is almost 900 millimeters. And it's almost certain that you're going to have more than 400 millimeters. It's unlikely that you get more than 1,400 millimeters. So this is the same thing you've seen before. Instead of having 3 categories, we have, if you wish, continuous categories. Another way to look at it is the so-called probability of exceedance graphic. So again, let's take the example of a farmer who needs 200 millimeters in the season for his crop to be healthy. If you look at the history, the black curve, he has 8 out of 10 years, he has those 200 millimeters. Okay. Now the forecast says that the likelihood to be above 200 millimeters is 100%. So he should be convinced that he's going to have a good season and it's going to be fine. If we go to somewhere where we have a drought expected, maybe back in Uruguay, you can see the tool is thinking because it's everything is done live. So I'm zooming over here. I'm going to click the driest spot on purpose. And you can see now the forecast has shifted towards drier condition compared to normal black conditions. So let's take again the example of a farmer who maybe needs also 200 millimeters per year in the season for its crop to be happy. So historically, 9 years out of 10, he has it. So it means historically he has one year when out of 10 where he could be in trouble. Now he only has 80% chance to achieve that. So he may want to consider how to consider this risk in light of this drier forecast. Okay, if we look at 250 millimeter, it's over 80% chance in normal conditions to be above, and now it's only maybe 60% chance. Okay, so that's a shift in probabilities that people can interpret in terms of risk to make decisions. Okay, so it's 11:15. I can go on with more map rooms, or if you want, we can have a break if you want to start a conversation. I understand we stop at 11:30. So whichever way you see fit, I'm happy to show more example of more maps and map rooms. Or
Please show more examples.
Okay. So let's see what I had listed here. So that was the forecast. So we have now so-called subseasonal forecasts. So this, what we've looked at, looks at seasons, and there's a recent development in climate science that tries to bridge between meteorology, which looks at the next 5 days, 1 week, and the seasonal forecast that look at a month and beyond. So the time in between is kind of a gap in forecasting climate currently, and it's being looked at now. I'm going to, let me check. It's going to be this one. Let's zoom out. You can see that the presentation is the same. But now we are forecasting. So the forecast made yesterday is forecasting the next 2 weeks, 30 October, 5 November. Sorry, the next week. So this is trying to reduce, to look at really what's coming up very soon. So it's a lot more noisy, as you can see. It's science in progress. We still have wetter conditions in Indonesia. I'm going to click that. You can see the same logic of terciles. So dividing the history into the third drier years, the third wetter years, and the third normal years, and here expressed in weeks. And so here the models are very confident that the next week is going to be way above normal. I mean, not way above normal, but it's going to be part of the wettest weeks on history. So that's the same thing, but looking at the next week level. I think I skipped. Yeah, I was there actually. Anyway, we can look at this. That's interesting. So changing topics a bit. I'm going to go into the climate and health map room, where you have some interesting thing about malaria in Africa. And for instance, this map called Seasonal Climate Suitability for Malaria Transmission. This is a static map that looks at 30 or 50 years of data, and it's telling you in a typical year how many months, so the times the color scale goes from 0 to 12, how many months are suited, climatically speaking, for malaria transmission. So we have an understanding of temperature, precipitation, humidity that is good for mosquitoes, that is good for the malaria parasite. So we can make this kind of assessment. So for instance, if you look in the middle of the Congo, you can see that it's dark red. So basically all year long, you have good conditions for malaria transmission. And so the local graphics are being generated. Again, it's thinking as it's making the query. And you have a white wheel on top of graphics that are still being refreshed. The definition of the suitability is that the precipitation be above 80 millimeter, that the temperature be between 18 and 32 degrees Celsius, and then that the relative humidity is above 60%. Okay, so we use those thresholds, we look at what happens in the month, and we say if it fits or not. So you can see that where I click in the Congo, all the three parameters every month, so you have the 12 months of the year from January to December, all years almost were in those thresholds. So, and the orange graphic is the convergence, aggregation of those three parameters. So that's why on the map, it's a 12 months red, dark red color. It's good for malaria always, and likely malaria is endemic over there. If we go to a more bordering part, let's go back to the cells. I talked a lot about it. I'm clicking here, this blue area. So it's only 1 or 2 months a year that are suitable for malaria transmission. And here we can see why. We can see that temperature is good always, except for April to June. But then we can see that precipitation is only good in July and August. Okay, so the superposition of those three things, relative humidity is often similar to precipitation. And so it's really during July, August, a bit September that we have climate conditions that suit malaria transmission in this part of the world. So again, this is where IRI can try to bring information. If you're someone who wants to control malaria, obviously what you care about is those months in June to October, where a shift in normal conditions in rainfall, for instance, could suddenly make a specific month of August or September more suitable for malaria transmission. So if your forecast says the next season is going to be wetter than usual, then maybe there is higher risk of malaria transmission. And thus, can I deploy logistics to be prepared for that, for instance? Distribute mosquito nets, medication if I have access to these things or not. So here we see clearly the role of rainfall in when malaria is best transmitted. I think if we look at Ethiopia, Ethiopia has a very dynamic topography. And we can see that there are areas next to each other that are very good for transmission and next to those others that are very bad for transmission. And that's because of elevation and temperature. So if I click here on the yellow dot, I'm going to see temperature always good, and then rainfall, three quarters of the year, rainfall is not bad for malaria transmission. Now, if I click the white button next to it, grid box next to it, I'm going to see suddenly temperature is never suitable for malaria transmission there. And that's because even though, I don't know if the map shows it, no. If we were to overlay a topographical map here, we would have seen that we went way up in elevation by going from this grid box to the other. So basically, higher elevation means lower temperature and then less malaria transmission. But again, that means a forecast that says hotter than usual coming season, does that mean that the warm temperature may be coming up the elevation and then in a specific season have this be suitable for malaria transmission? So that's an interesting tool, I think, to look at. Let me see if I have more in mind. Okay, we can look at the locust one, maybe to conclude. You may remember, I think it's within a year or two, there were big locust infections in India and in Northeast Africa, like Kenya and so on. You may have seen that in the news. So we have some tools that help look at this, that look at rainfall, and that. So you may have noticed, I'm looking at the chat. Yeah, well, so when it comes to rainfall predictions, there's not much to say about the Sahara because there's not much rainfall there. So unless you look at weather patterns and see some perturbations that go through the Sahara, then you may have things to say. But if you average over seasons, then basically there's nothing to say about the Sahara. What you can be of interest is maybe some marginal variability at the border between the Sahel and the Sahara, where rainfall can push up north of more than usual or not. And there you can have things of interest to look at. However, the locust business is typically happening in the desert when there is some rainfall events that happen and create conditions that are good for locusts to develop. So an illustration of that is this monitoring tool that looks at what is called NDVI, Normalized Difference Vegetation Index. So it's an index for vegetation. And actually, let me go to East Africa. So what folks do here from the FAO, the Food and Agriculture Organization, that they look at this, it updates every 16 days. So the last time step here is September 30th to October 15. So probably in a couple of days, we'll have the next 2 weeks. And you can look at very fine resolution data and potentially spot wet or green areas that where you might want to send folks to explore if there are locusts breeding there. You can see it's very high resolution. And I think the other tool called Greenness Estimates is trying to give a sense of anomalous patch. So they might want to send folks there to see why it's specifically greener than normal in this area. Okay, so this is not climate data, it's vegetation. But so that's part of the game. Okay, it's 11:27, so I think I'm going to stop there. I don't have very concluding remarks. I think you can guess that I could go on and on. There is a lot more map rooms in there. Again, my point was that I believe that some of this you can probably send your pupils to collect data, make visualizations, click on maps. If you have any questions about these or others that you are exploring, remember that you have help@IRI email that will go to my team, or you can write me, remic@IRI, and we'll be more than happy to give you a hand with things that you want to do. And that's it.
Remi, thank you very much. One of the nice things I was thinking about in here is that with the next generation science standards, we want our students to be able to create problems and find answers for them. So here you have a whole bunch of resources available to you for students to look at some world problems, start thinking about possible answers. And I know Remi well enough to know that if you send him a message, he will definitely get back to you. One question I have for someone on here, who is the 646-286 number?
Mike,
Yes,
hey, this is Kathy. I lost the sound on my computer, so I had to call it in.
okay,
I'm sorry, my number keeps flashing all over the place.
so that's you,
Can we get rid
Kathy.
of it? Yeah.
I
Sorry.
just want to make certain when I send out the certificates later that I haven't missed
Okay.
anybody.
Yeah, all right, but just if you can, get rid of my phone number. I don't know how to do it.
No problem.
Otherwise, I'll hang up.
It's not a problem.
Okay.
Okay. Anybody else want to make some comments about how you might be able to use this with your students?
Maybe they need to digest a bit.
Right.
Well, it's all there, so you can go back to it, explore it at the pace you want.
Thank you very much, Remi.